Good morning to one and all. A very warm welcome to 8th ISET webinar by Professor G.R. Reddy on structural equipment, piping interaction under earthquake excitation. We received overwhelming response. More than 750 have registered to this webinar. We thank all the participants for registering and contributing to a noble cause. Before I introduce today's speaker, I would like to make some announcements. We request all the participants to kindly mute their mics. Also, please stop your video to minimize bandwidth usage. Please do not annotate anything or request the speaker to allow screen sharing or any such thing. Question answers will be taken at the end as usual. Chat window will be enabled towards the end of the lecture. Please restrain your questions to the end. Participation certificates for the last webinar have already been issued. Even though we are announcing our policy in this regard to issue the certificates, we are still receiving some requests after the seminar. Participant certificates will be sent to only those who attend the webinar from the start to the end. Attendance will be taken in the hour and the of this lecture. So please mark your attendance over Google Form. Certificates and feedback forms will be circulated to only those who gave their attendance. Inconvenience caused in this regard is regretted, particularly we apologize to your members. We are following this practice so that we don't want to encourage our students to misuse these certificates. Now I would like to introduce Professor G.R. Reddy. He is currently an adjunct professor at NIT Karnataka, Surathkal, and formerly outstanding scientist, senior professor, Homi Baba National Institute, Baba Atomic Research Center. He has obtained his PhD degree from Tokyo Metropolitan University, Tokyo. Since 1984, Dr. Reddy is working in the area of structural dynamics, earthquake engineering, and analyzed, designed structures, equipment, and piping systems of nuclear facilities. He made significant contributions in design of 500 megawatt PHWRS and involved the design of AHWRS. They are related to the reactors and also involved in the design of structures for solar thermal power plants. He made contribution in the design of 30-meter DSN antenna for Chandrayaan project and recently completed the design and construction of large size gamma ray telescope. He worked in the research areas like modeling techniques of complex structures and developed beam model procedures using energy structural equipment interaction into earthquake and developed decoupling criteria for multi-connected equipment, stochastic models, and dynamic substructure techniques, etc. He has made more than 500 publications, including journals, reports, conference proceedings to his credit. He has guided 10 PhD students and 41 MTech students from various institutions. He has published a textbook on seismic design, structures, piping systems, and components, published by Springer in 2019, co-authored with Mr. Hariprasad and V.K. Verma. And he has also contributed several book chapters. Overall, he has very vast and wide experience in various fields. With this brief introduction, may I now request Professor Reddy to deliver his lecture.
Thank you, Dr. Ravi. Thank you very much. At the beginning, let me say thanks to ISET for giving this opportunity to deliver lecture on structural equipment and piping interaction due to earthquakes. And a special thanks to Sri Valsa for personal invitation and to deliver this particular lecture. So good morning to everybody. Now the topic is on structure equipment and piping systems interaction due to the earthquake. I think 1 second. Yeah, structure equipment piping interactions under earthquake excitations. So already you have the introduction. Now, just briefly, I want to say about interactions. I'm sure all the participants have some amount of knowledge on the basics of earthquake engineering and structural dynamics. I presume that if my presumption is definitely correct, then the interactions what I meant is that when the structure, equipment, and piping are coupled together, the dynamic characteristics, including the free vibration characteristics like frequency, their participations, even responses for a given excitation, is different than if you try to do analysis or try to calculate the responses, dynamic responses individually, like structure separately, equipment separately, piping separately. So that's what I meant, the interactions of structure, equipment, and piping under earthquake loading. So this brief idea you should keep in mind about interactions due to the earthquake. Now I'll just briefly explain about what the equipment, what are the piping systems I am keeping in mind to explain the interactions of equipment, piping, and structures. So generally we have non-industrial systems and industrial systems. We can group into two. The non-industrial systems like residential buildings and connected services, maybe the water supply system, drainage system, then you have the fire water system, and other non-structural elements each house has. That's total thing we call as a system. Then offices, similar to the houses, maybe the difference is the people and the kind of non-structural elements in the structures will be different. Then institutions, again you have the laboratories apart from classrooms and so on. So this we group as a non-structural non-industrial systems. So in this non-industrial systems, you have most of the non-structural elements. Say, for example, if you have taken the classroom, you have a chairs and desks. And also if you take the laboratories, you have a good amount of testing equipments, particularly if you have a engineering institute, then you have if you visit a heavy structural laboratory, you have the actuators. You have many components and systems which are used for the testing of structures or other parts of the related elements. Now when you come to the industrial systems, you have the manufacturing industry, then you have the process industry, you have the power industry in groups. I'm not going to talk, it's very difficult maybe to talk about all the equipment, all the piping systems of all kinds of industry like manufacturing, processing, and power industry. Even say non-residential, non-industrial systems also, if you want to talk everything, is very, very difficult. But whatever I'm trying to explain through various slides, you can easily extrapolate the situation for your specific industry, and you try to see that how the things, whatever I'm going to explain, can be used in the future designs or even current designs, and ensure that the safety of the structure, systems, and components for a given design earthquakes are safe. Here it is. Now I'm explaining about non-industrial systems. So these are some of the pictures I've taken from my house itself, so that to explain is very easy because everything is I know very well. Now some pictures, maybe the hospital downloaded from the internet. So if you see, the first slide, you have say TV. So we can say non-structural element, but is also important for many aspects. Then you have the say fridge, you have the say washing machines. These all called, in engineering sense, we call equipment. Say if you talk about the TV for electrical people, they say electrical systems or electronic system, they say. And this is non-structural. When you talk about structural engineers, they refer these all as a non-structural elements. But if you refer to the mechanical engineers, they say these are all equipments which are also meant for your daily life. Now coming to the hospitals, very important. The beds are very, 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 very important. I think today everybody is well versed with the hospitals because of COVID-19, and the importance of this particular facilities for treating the patients are very, very important. Now see how we relate with our equipment structure and piping interactions with respect to the hospitals. Now we have the other kind of furnitures which may be fixed, or it's just generally kept. These all non-structural elements freely on the floor, or sometimes it's sometimes they are locked. Particularly if you talk about the wheelchair, it is easy to move. Then you have a locking systems, but generally that locking systems also have certain limitations. So that's how you'll find in the non-industrial systems, particularly if you talk about hospitals and houses. These are the equipments what I'm referring to. Now I just given central two figures. One is these all, whatever the equipment we are talking, non-structural elements we are talking, it is very, very light, equipment. Like, a boy on a father, on the top of father, the father can carry, this, son any long distances very, very slowly without much problem. So this load is not definitely felt by the father because the weight of the, his son is very, very small. His child is very, very small. Similarly, it's also we can treat the structures, whatever the structures we design, maybe the non-industrial structural system. It is like you can compare like elephant. See, for example, if you have 100 square meter area of the house, maybe you have about 10 tons total area is occupied. So it's very, very small load compared to its own weights. That's what I'm trying to say. Now, if you talk about the interactions, see in the dead weight also, it's not going to contribute significantly into the stress limits or the loads on the members. And same time, this if the there is some kind of motion in this particular elements, then also you'll find that the structural response not going to say very change much, because the weights of this particular non-structural elements or equipment very, very small. That's what we say. We always compare with the elephant. An elephant, if you sit 2-3 people, the elephant is not going to feel anything with in terms of the load. But what happens if the load increases? That's what we are going to talk in the next slides. So I try to compare whatever this non-structural components in the, say, non-industrial systems are not so heavy. They are very, very light and is not going to have the effect on the structure, but definitely the structure going to have significant effect on the behavior of this particular non-structural element. That's what I want to convey from this particular slide. Now it is about the piping systems. I think nowadays the piping systems are very, very important, particularly the water supply systems and even fire water systems. Fire hazards are very large nowadays. The firefighting systems, fire headers, everything is generally is a part of your building designs, and it is building layouts. It is a part of building layouts. It is compulsorily you have to have this kind of systems. Now, during the earthquake, you have to have some idea how to design this. And today, I think IS 1893 code is being developed, part 7, on equipment piping systems. Otherwise, we do not have well-defined and design codes for equipment and piping systems. Elsewhere, in other parts of the world, you have some amount of design codes, but in our country is being developed. How this particular important piping elements, how they are going to interact with the building. For example, you say here the piping is running from the ground, from the tank to the elevator tank. It is going through the various floors. You have a displacements of the pipe as well as inertia of the pipe. So you have to generate these inputs if you want to design this particular water supply system. Particularly the fire water system is going to be very, very important, because we are expecting fire hazards after the earthquake, during and after earthquake. The secondary hazards are going to be definitely there in the present scenario of the sea, because the power consumption is very large, and in the same time we have the buildings with the gas power supply, gas supply, etc., etc. So safety is very important. If you want to take out the safety aspects, this piping performances during and after earthquake very, very important. So now, if you see this piping system, so you have the water piping in the one side, other side you have gas, piping system. There looks very, very simple. It's not going to definitely change the overall behavior of the structure, but definitely the safety aspects. If you want to ensure the safety after the earthquake or during earthquake, you have to see these small elements also has to perform as per the desired performance limits. That is, it should not break, should not leak. That is one of the performance levels so we look for from this particular, say, piping system. Now, coming to the hospitals, I think, say, for example, even say, for example, we are not expecting the earthquake when the COVID patients are treated in the, say, zone 4 and zone 5, some earthquake has to come and this lifelines has to disturb. We are not expecting, we should not wish that. But if such situations happens, this all, in life-saving piping systems are very important as to survive, and it has to, deliver what expected, oxygens and so on and so forth. So that way is very, very important, even piping systems, even hospitals also. Now coming to the institutes, you have a lot of equipment. Sorry. I hope you are hearing. So the institutes have a lot of testing equipment, and also you have a lot of active, say, for example, power packs. Then you have the piping for the actuator supply of the oil, and you have large kind of systems, even equipment and testing systems in the, say, institutes. So you have to consider proper design inputs and ensure that these all systems also safe. Though it is, people find it may not be that significantly, it has to be looked into, but still very, very important, as I explained. And again, the central picture shows that these also have very lightweight, is not going to have much effect on the behavior of the structures. Now, let us go to the industrial structural systems. Industrial systems. Industry has, a lot of huge equipments. So I'm from the, I was working in the nuclear industry, so I have taken the pictures from the nuclear industry, like, 500 megawatt reactor building. So if you see the reactor building, also similar to that, you have also other industries. Just we'll talk about that also. You have a huge equipment, like, for example, say piping, pumps, then you have steam generators, you have reactors. You can see the size of the reactor. For example, the total weight of the reactor will be something around 1400 to 1500 tons, which is supported on a structure has about maybe about 8000 tons. So you have a significant mass ratio with respect to the supporting structure to the equipment. So that is a good example. I can always say such kind of equipments are very, very common in most of the, say, process industry or power industry, or even is a manufacturing industry. So this is good pictures which shows, you see how that, occupied the space of the whole structure. You can see if you go to this, any reactors, you'll find most of the area is totally packed and with the huge equipment and piping systems. Again, piping system may not be having much effect on the behavior of the structure, but definitely this kind of huge equipment will have significant effect on the structural behavior. So when I talk about structural behavior effect of the equipment, again, I'm referring to the interactions in terms of the frequencies, then participations and the responses, dynamic responses. On the right side in the corner, you have the cement industry. The kiln, then you have the supply. If it is a dry process, then you have the slurry is going to be supplied to the kiln. If it is a wet process slurry, in the dry process, your powder has to be supplied. Cement powder has to be, lime powder has to be separated to the kiln for the further process of the formation of the clinker and so on and so forth. But if you see the structure and supported ducts, the ducts are very huge. Is obviously you can feel that these ducts are, piping kind of systems, definitely going to have a significant influence on the behavior of the supporting structure. So that's what I wanted to say, that in the industrial, systems, you have huge equipment which has a definitely significant effect on the behavior of the structure, and vice versa. When the structure is affected, same time the inputs coming onto the equipment or piping system also going to change. So the interactions on either side is possible if you have very huge equipment on the, say, structures of the industries. Now that's why I just trying to compare that, if you have an elephant and it's trying to carry huge load, definitely it feels it cannot walk faster when you have only 2 or 3 people sitting on it. But if you have a large weight, then definitely feels, and it will slowly go. But now suppose this, I try to explain here in the previous slides also. If the person, when you have a huge weight and trying to go very fast, definitely the person carrying it finds little painful, is very, very difficult. Now the speed definitely going to have some kind of effect on the, its resistance, to carry such kind of heavy load. Similarly, elephant, when it's trying to carry huge loads, it has to obviously has to move slowly. If trying to move, definitely it also feels some kind of pains or some kind of difficulty to go very fast because of huge load on its back. Similarly, now if you come to this particular equipment, when the this equipment is because very huge, it also has good amount of mass, and that along with the mass, it also has a good amount of stiffness. That means the frequency, it has certain frequency, and same time the structure also have certain frequency, certain inertia. If they are very close to each other in terms of mass, in terms of the frequencies, definitely the reactions transfer onto the structure will be different than independently when you try to calculate without considering this kind of huge masses, including the stiffness and the inertia. That's what we are going to talk more details in the few slides coming. Hope you are getting the subject very slowly. What I meant is equipment and piping system with the structural interaction. And if you go very details inside the plant, you'll find huge amount of piping systems, and you have obviously have a huge components in the nuclear facilities. And same thing is true in most of the industries, as I explained, for example, with the cement industry. And those are working in the industries, they can easily understand what are the such kind of components prevailing in the various industries. Now, to have the if you are clear with respect to the non-industrial systems and industrial systems, and respective equipment and piping systems, if you are clear. Now, if such kind of systems are subjected to the earthquake, I think earthquakes you all know very well that we have the crust has a weaker planes, and because of the tectonic characteristics of the earth, there is a stress built in the weaker planes, particularly other part of the crust. Also, you have the stress, but weaker plane has a less limits of bearing capacity or bearing stresses. Once that exceeds, there is sudden amount of sudden release of energy. The waves propagate from the crust, maybe about 10 kilometers or 15 kilometers, even sometimes 20 kilometers from the depth. It will come to the surface. Then also try to excite the local, waves like relay waves and the P waves and shear waves, and generate the relay waves, and that waves are trying to have the ground displacements all together combinedly. Maybe the time of occurrence may be the different. I think that details we no need to talk. I think earlier speakers must have talked about these wave propagation and causes for the ground displacement. Now this causes the ground displacement. The ground displacement when it's having function of time, then you have acceleration. For the convenience, we take accelerations in order to evaluate the response of the structures, equipment, piping systems. Now, if you see here, so I'm just giving a typical industry. You have a structure, and structure supports the equipment. Okay, then equipment to the equipment other side. When it is support on the ground, you are connected with the piping system for the flow of water process fluids, and some ventilation ducts also connect to the chimney. So these are all going to get excited. If the design is not adequate, there are these particular components or piping systems getting opened, and whatever things are carried, it is going to be coming out of the say systems. And if these are very poisonous, then it's going to have definitely good amount of effect. I think good example is LG polymers, whatever you have seen recently in Andhra Pradesh, Vizag. So such kind of accident takes place, then you have a big risk because of the industrial systems when they are subjected to the earthquake, and if the design is not adequate, then there is going to be such kind of problems. Now design is only the design is not enough to say that the risk is very high, but you have other parameters like decay parameters, particularly the aging effects of the structure, systems, and components also has to be considered. If you want to evaluate its risk and its fragility, its capacities, and so on and so forth. So that is a different aspects. What I want to say that when the this particular industrial systems are even say residential systems or non-industrial systems are subject to earthquake, then you have good amount of forces, stresses develop. There's a possibility of failures. If you have the better design, adequate designs, you are safe, and the risk is very, very small. Now, generally the earthquake motion, as I mentioned, is represented as acceleration versus time. So typical ground motion history, that is not actual earthquake, but it is a artificial earthquake motion, whatever I've shown in the right down side, which is a random excitation. The frequency typically is a 0.1 to 50 hertz. Earlier days we used to talk about 33 hertz. I'm sorry. So earlier we used to say the rigid frequency 33 hertz. Today we are talking even 50 hertz. Some places people talk about 50 and 100 hertz also as a rigid frequency. So the frequency content of the ground shaking, say acceleration ground motion, will be about say 0.1 to say 50 or 100 hertz today, as per the understandings. Now it is a very random signal, so that is going to be as excitation for this industrial or non-industrial systems, how they are going to behave. Then we have to understand how they are going to interact, this equipment, piping, and structure. Now here I just want to say show some slides, some films. Yeah. Say in the case of hospitals, as I mentioned that they are not going to have a big effect on the structure, but its own behavior is coming because of the interactions of the structure with the equipment system. See, hospitals, whatever the let's say beds you have, then you have the monitors, many other things in the hospitals. If they are not properly anchored, and structure definitely is going to excite significantly. Excitation also depends upon where these are located. So you can see that you can feel the problem that the non-structural elements, whatever are there in the industrial, non-industrial systems, very, very important with respect to the local safety, local risk is concerned. Suppose you have a cupboard and the earthquake has come in the night, for example, and your cot is very close to the, say, cupboard. And if the cupboard is not able to see its stability and it simply is going to fall under the bed, the people are sleeping on the bed, there is a risk of their life. So what I want to say, these non-structural elements, though looks very simple, but you have to definitely take care, and you should have proper design of these things. And if you want to design, you require to have proper inputs. That's what we are going to talk, how to generate proper inputs considering the interactions. Now, when you come to this particular slide, when you say that, these are definitely not going to influence the behavior of the structure, but the non-structural elements going to have an influence because of the structure and the location where these non-structural elements, which level it is located, is a first floor, second floor, or third floor. The excitation levels are going to be different at different levels. So structure definitely going to interact with these non-structural elements and try to push the behavior as per the behavior, characteristics of this non-structural element. Similarly, you can see other, say, non-structural elements, whatever photos I've seen on the downside on both the hospital side and say houses. Now, if you go to the next slide, what I want to say, it's all non-structural elements. You have a very, very simple solutions. It's not that you should have very, very detailed designs if you want to make it. It's possible to design. You have to have good amount of calculations if you want to say that these are going to be safe, though it is very, very light system, as light, say, components or equipment. One simple solution, you should have a good friction pads and stoppers and floor grippers. Then you will not have that kind of motions what you have just seen before. And you also can have wall anchors with a good amount of friction pads. But if you want to design, if you want to ensure that this is going to function properly for the design-based earthquake, this designs definitely you have to make with respect to the location of this particular non-structural element, the components in the building, and you should have proper inputs based on the location of these things. Otherwise, simple solution definitely helps. Maybe these all things may not be required up to zone 3, but zone 4 and 5. Definitely this kind of solutions you have to work out and implement in the non-industrial systems for the equipment and piping systems. It is like, I try to show one picture in between. I think we have how the child is carried by mother. So definitely you see how the hand is, try to give the good support and try to have a hooking the child so that child is not definitely children are very very naughty, that's obviously. So this is what you have seen, this equipment when they in the hospitals, in the houses or in the offices, how they are going to behave is very difficult to predict the behavior, very very I think chaotic, we can say that. But if you want to do numerical calculations, is very very difficult task, let me say. I think maybe somebody tried to say that I can definitely do that. There is a difficulty to compare exactly the behavior, such kind of highly very highly non-linear when you are at the younger age. So what I want to say that if such kind of things obviously going to be there, then if with the small measures like this, we can have the better safety and better performance of the equipment and piping systems in the, say, non-industrial systems. So now coming to the piping systems, again we are talking with respect to the, say, non-industrial systems. You have obviously there is if you do not design properly, so this particular piping system is going to have difficulty and failures are obviously there. Now when you come to the, say, this particular, say, water supply system, let us assume that this is a fire water system, and we are expecting the fire hazards during and after earthquake, because maybe the gas connection problem, or maybe the, say, electric short circuiting, many other reasons possible to generate the fire hazard. And if you do not have the functioning of this particular water supply system, fire water supply system, then you are going to have a big risk. If you want to ensure this fire water system going to be functional during and after earthquake, then you have to design this piping system very carefully. Even tanks you have to design carefully in order to ensure even after effects of the earthquake, like fire hazards. So it's very important. Now, if you want to design this kind of things, you should have proper inputs, proper design inputs has to be generated carefully. In that way, the interaction is going to play a very, very important role. That's what you will learn further, even very deeper way. Now, this particular slide, I always like to, present. I think many people, if heard my lecture earlier, also definitely must have seen this slide. The reason I always present this slide, of course, in this only I put one slide, but you have many slides of similar kind. So you have on the right side, the failures during Kobe, because I always take Kobe as a reference because I had a chance or some opportunity to visit after earthquake. During earthquake also I was there, but away from the Kobe. So I took a lot of pictures. So I always keep that pictures on the right side. On the left side also I had a opportunity to visit the Bhuj earthquake. You can see the comparison of failures. So you have the failures are similar. If you see on the left side, we have the temples, there's a failures. On the right side, you have a shrines in the Japan. So these are failures. So bridges, same failures in other side. Say like electrical battery system in the industry. Here also similar kind of failures. Pipings also similar kind of failures. And you have the similar kind of failures even in the case of say big equipment in the industries like this. What I want to say that, see, always people will have that, India is very stable country. Don't worry, no need to worry much about earthquakes. But please remember that the design inputs, design levels, what we consider is much, much smaller than, like, for example, Japan. Now, like, even if you talk about in the country itself, we have a zone 5 is a maximum considered earthquake 0.36Z. If you come to the zone 2, you have 0.1. So you have a large variation. But you are going to design with that limits, right? So when you are designing your, structure systems and components with that kind of design basis, then you have the capacity to that level. So when the earthquakes happens, say it just exceeds the design basis, or sometimes the aging effects I was mentioning is weakens the structure, there are going to be failures, right? So the failures should be similar. It's not that you have the highly earthquake prone area, you have the problems, not the other side. It is going to be the problems are same, which you can see from this slide. So what I want to say that whatever the extent design basis, whatever design hazards are mentioned, and is also going to help. I think I want to say some more things here also. If you design the any non-industrial systems or industrial systems for the given earthquake basis, then it also going to help for, say, other hazards like blast. because it has some inbuilt capacity for taking the dynamic loads. Definitely is going to help, even though it is not properly taken care of the unexpected blast and all. But because of the design is done with the earthquake, definitely you have good amount of resistance. So that way also it's going to help for other hazards also, if you try to design the structural systems or equipment piping system for earthquake. So we have a secondary benefits also if you try to do the designs properly for a given earthquake motion. So some more failures again, so far I talked about the equipment and piping systems are connected inside the buildings. There are piping running from building to building also. Some portion of the piping also runs on the ground, and major equipments also there on the ground. So when your equipments are there on the ground, then the definition of structured equipment and piping interactions are not directly related to this. Is directly it is sitting on the ground. The obvious interactions are with the soil. So if you have a good soil, you have a good strength, and the design is properly done, then contribution of the soil onto the behavior of the structure and vice versa, structure to the soil will be taken care, and the safety. Called the elephant foot buckling, because it has a sufficient hydrostatic pressure. Then you have a dynamic loads because of the shaking. The two interactions will try to have the elephant foot buckling kind of failures. Very common in the case of very huge tanks in the industries. And you have the cranes in the ports. So ground, because the rail behavior is going to change because of the ground capacity, and it's going to be dislocated from the rails, and same time you are going to have the huge forces coming from the cranes, that also going to have the effect on the behavior of the soil. So you have a good amount of significant interaction between the equipment and the soil that leads to the this kind of failures if the design is not adequate. And same time also you have to keep in mind the aging effects. Aging effects are going to be very, very important to say that the failures are just because of earthquake and design is not adequate. Always we cannot say the inadequate design only created problems. Maybe because of the aging effects, sometimes going to have the significant effect on the behavior of this kind of equipment. And again, piping systems, say pumps, and the connections between the adjacent components. You have the elbows and sometimes the flanges. They're all going to be obviously going to have a lot of failures if the adequate design, adequate maintenance and life is taken care. Unless if you don't taken care, then your failures are going to be there. And fire is going to be definitely going to be a problem nowadays in the modern world. These are going to be there, so we should get prepared. And our systems, piping systems, and the connected water tanks, water supply system should be properly designed and ensure that safety for the after effects of the earthquake also. Now let us see how the important is. Yes, we talked. I hope all of you got convinced that is very, very important to have the better design of your non-structural elements. As per the definition of the structural engineers or mechanical engineers talking about equipment piping systems, it is very important. In this talk, we are not talking about electrical systems, but similar kind of knowledge can be extended to the electrical system and try to qualify those electrical and electronic systems also. Now, if you want to design these things, you require to have the proper inputs. Now, the equipment or piping systems are just sitting on the ground. There is no issue, because whatever if you talk about our country, ISET 893 spectrum for different zones of the country already well defined. You can take those things and directly design the ground-mounted equipment and piping systems without any problems. But the detailed efforts are required when you want to design or you want to ensure the safety of the equipment piping systems when they are mounted at different floors of the building. This particular slide shows the simple concepts, how you are trying to generate the inputs for the equipment, floor-mounted equipment and piping systems. We have a design time history, design-based time history. Now, I think there are some gaps in our the gaps that are going to be filled in 1893. We have the spectra, but we do not have compatible time histories. But in the part 7, we're trying to put some efforts to generate compatible time histories for the design basis response spectrum for various zones with different soils like soft soil, medium soil, and hard rock. We try to generate compatible time histories, and we are trying to give in the 1893 part 7. So if you want to do the calculations for the inputs of the floor mounted industrial floor mounted systems and components, same time is when I say industry or non-industry also, when you talk about the say fire water piping system or gas lines, even certain important equipment in the institutes also you have to generate proper inputs. For that you require to have some kind of time history. Now I'm going to explain not only with the time history basis but simplified methods, coefficient methods, some details I'm going to deal with respect to the proper generation of the inputs for floor mounted equipment and piping system. So first step is you should have a structure, then you should have a details of the equipment piping system supported on the structure. Then the equation of motion obviously have the inertia, damping, and the stiffness is equal to the applied force due to the earthquake. See, now question comes, if you are able to today, I think you have fast computers and people say why we have to talk about the interaction, simply model everything existing in the plant. That's generally whatever the computer speed you have, whatever the computer you have, but still it is not possible to have a complete information of all the systems components, even structure in the beginning of the design of the plant. So obviously you have to consider some kind of assumptions. You have to have decoupled way analysis has to be generated and the design has to proceed, that you cannot avoid. But there are certain components, as I mentioned, has to be considered. Once everything is available, then you have to check back that the effects of interaction of this big equipment on the behavior of the structures and vice versa. That's what we will be talking a little more details now. So equation of motion very clear. So you have the time history, then you have models of the building, then you can have the different floors you can generate what are the time histories, because this is obviously the equation of motion is function of time. Then you can have the time responses at different floors, like floor accelerations versus time. Again, if you have this particular information, you can use the single degree of freedom system to generate the spectrum at that level, and that spectra you can use for designing of the floor mounted equipment and piping system. That is the whole philosophy go on in order to generate design inputs for the piping and equipment system. But there is some kind of flatness. That's what I'm going to talk a little later. What is that flat portion of that? So now that is a philosophy how you are going to generate. One philosophy I try to explain. So you have to generate the inputs for the equipment piping wherever it is generated by structural analysis. There are various methods. One is direct method, design spectra to time history. You can directly generate flow time history. From there you can generate the spectra. And when you are trying to generate time history, obviously you have the integration techniques like Newmark beta, Wilson theta techniques you can use to solve the above differential equation and get the time histories at different floors. And once you have the floor time histories or support location time histories, then you can generate spectra from that time histories. That is a direct method. Other method is design spectra you can have, because when you are making the design spectra, it resembles as ensemble of the earthquakes. Therefore, you can also have a design power spectrum correspond to whatever the time histories we consider to make the design spectra. And you can have the stochastic approaches or random vibration approaches to generate the spectra directly from spectra to spectra using the power spectral density conversion from the design basis input motion as a response spectrum. Now you have the simplified methods. Now simplified methods you have, directly you can go from the spectra to spectra. We have a direct method as considering a single degree of freedom oscillator. Each mode of the multi-degree of freedom system structure is considered as a single degree of freedom oscillator, and you calculate the response spectra for each single degree of freedom system representing the structural modes. Then you can combine to get the spectra for all the frequencies considering all the modes of the structure. So you have a direct method. This is one of the maybe the very useful technique for most of the industries. I'm going to deal something on that also. You have a little bit conservative and non-conservative, but to have the initial designs, you can also use the approximate method. These methods we are very clearly we are mentioning in the IS 1893 part 7, so that you have the clarity on the design inputs what to be considered for design of the floor mounted equipment piping systems. Part of that particular code I'm going to present here. Now again, I brought back here the same thing, direct method. You have the time history. Now compatible time history, I'll just speak a little bit on that also. We have the time history on the right side, xc double dot with respect to time is given. Then inertia and damping and stiffness of the structure is on the left side is model. You solve this differential equation, get the time history. So you have the usual, time history analysis to get the flow time histories, and from the flow time histories you get the response vector. That is true in, say, I also shown on the right side with the nuclear industry how the people do it. Now, just little bit concepts of the response spectrum. I'm sure everybody knows about it, but for completeness, I just have to have the continuity. I'm just presenting this particular slide. So you have the, say, for example, on the ground mounted tanks, overhead tanks, if you are able to represent as a single degree of freedom system, when you pass the design basis earthquake, I think here we have shown the L center earthquake, doesn't matter. Say the same is also, you can consider whatever design basis compatible time history as input. Then you can generate, excite this, and you can see the response. For example, in the left side, whatever tank example I've taken, you can see what is the acceleration very clearly. And also you can see the response. I think very clearly you should understand here that whatever the random signal we are talking about, 0.1 to say 100 hertz or 50 hertz, is all going to get filtered. And finally, the response of the building will have the very frequency content equal to the natural frequency. That's what you can see very clearly. It goes more towards the sinusoidal characteristics. When you pass this particular random signal to the structure of a single degree of freedom system characteristics, you have the only sinusoidal characteristics of the responses. So other frequencies are filtered out because the structures behaves like it filters for a given excitation with the random frequencies. So this is, if you take a single degree of freedom, you have certain, say, response as shown here, and you have other, tank, but it has a different frequencies, then you have the different response. So if you are having the different frequency single degree of freedom systems, then you can have the responses, maximum response you can pick up as explained on this slide. If you plot those maximum response with respect to the time period is what we're talking about, the response spectrum. I think these concepts, I'm sure many people, maybe for beginners, this will be maybe useful. For the experienced people, maybe again, you are recollecting your experiences. So what I want to stress on this, that, when you talk about the characteristics of this particular, responses, you have some kind of peaks on the response spectrum that correspond to the natural frequency of the single degree of freedom system. That's what I want to try to, explain here, and the procedure of getting the response spectrum. Now, obviously, same kind of concepts can be extended to the equipment again. So it doesn't matter. Response spectrum is not specific to the equipment or piping. It's simply representing the single degree of freedom system with the different time periods or the frequency of the, equipment or structure, whatever it is, but representing as a single degree of freedom system. Now, when you want to try to do this particular chemistry analysis, whatever we are trying to show with respect to L center earthquake, when you talk with respect to the 1893, so this particular, spectra is 1893 spectrum. Now, you can see here that, 3 time histories, compatible time histories we generated. When you try to use these time histories with the procedure I explained above and try to generate the spectrum, you can see the blue curve that is called, spectra from the realized or from the artificial time histories generated with the concepts, whatever I explained. Now it looks, they are very closely comparing. It's impossible to have the same 100% comparison with the design basis, but there are certain procedures to accept these time histories are acceptable or not. See, very conservative, you have to see that all points are above the design basis is good, but it's very conservative in most of the cases. Unnecessarily, you are penalizing the designs. But, some points can come down, then some points can go up, so that the energy contents of the, design basis spectrum and the, artificial time is maintained, then it's very good. But you have very specific guidelines, which we are giving in the part 7. You can just follow that, then ensure that the compatibility of the similar kind like this. But this time is we are planning to give for everybody in the section part 7, so that people can use it, or otherwise we also given the procedures how to generate the artificial time history. You can generate your own time histories compatible to the design based response spectrum. So once you have the time histories, then definitely you can have the flow response spectrum having the proper modeling of the structure. Now, the other method is we are talking about the spectra to spectra generation. So what you have in the place of time histories, you have the input as a response spectrum. maybe the rock sites or the medium sites or the soft soil site. I just shown for the medium soil and rock soil sites. Then you have the model. From this, how to generate, that's what we are going to generate. We are going to explain, because this method is very handy for the designers. But the first one, direct method, generating the compatible time history, is a lot of subjectivity is there. And the code also taken care that subjectivity is that you should have minimum 3 time histories. The average response spectrum should be compatible as per the procedure given by the codes, so that you can accept those time histories for doing the time history analysis. So now coming to this direct method, say I'm not talking on the stochastic method. So simple steps is you have a compatible power spectrum to the design-based response spectrum. Use the random aberration approaches. Then you get the mean values of the response at different single of freedom system frequencies at different floors, and try to have the response spectrum at different floors. That's very simple to explain, but we also trying to give this methodology in the code also. Please, you can go through that. And those who wanted to learn more and more, they can obviously write to me, or you can see the lot of references, lot of books available to understand the process. Because I think we have limited time to speak, so I'm not speaking much time, all the details, but I'm just giving the glimpses so that you also have idea that you can generate your design inputs for equipment piping system with various methods. I always suggest if you have a stochastic method, if you see the response spectrum, they are very, very smooth compared to the time history methods. Because obvious reasons is that you are always, when you're doing the response, you are trying to average kind of response you're going to be here. Get the, from the methodology, you always get average responses. So that helps to have very smooth and, design inputs if you follow the stochastic methods. But anyway, please go through that. I think the code or draft version also explaining all those things. If somebody wants specific explanation, you can contact me. Now, coming to the direct method, you have the model, then you have the response spectrum. It is not the ISET 89.3, but some kind of site dependent spectrum like Tarapur site. This input is there. Then how to generate, that's what I'm going to tell. You should have the input, then you should have a model, again the natural frequencies and participation of this model. So you have that. The simple equation, I think, whatever, I hope you are able to see this equation. The equation is a function of your frequency of the, structure, and the frequency of single degree of freedom oscillator, and damping of the structure, damping of the, oscillator, for which you want to generate a flow response spectrum, or the equipment support response spectrum. If you want to generate, consider the equipment damping. So that is the another parameter, damping of the structure, damping of the equipment, frequency of the equipment, frequency of the structure is considered there. And based on that, then you can calculate what is the response, maximum response in that particular mode for that degree of freedom with the given damping. You can calculate from that equation. Then you can also take the modal effects of the structure by taking the response for a given single degree of freedom system and combine with using the second equation to get the maximum response of the single degree of freedom system, considering all the modes of the structures, okay, and the frequency. When say all the modes, its frequencies and participations also taken into consideration. Then you can see on the right side how the spectra is generated. So it is a comparison between the time history and the direct method. So direct method is giving little higher than the time history method, but the shape, the characteristics, you will find very similar to the whatever procedure, whatever the spectra you are getting from the time history method. Now here you have to note down that there are certain peaks in the response. That peaks are correspond to the natural frequency of the structure. So in all the floor mounted equipment, response spectrum, whatever you are getting from the structural analysis. So you'll have the characteristics that the peaks are going to happen at the structural frequencies. That's very important to talk about the interactions in the next in the presentation. So now that is one method where you can use to get the response spectrum directly by knowing the modal characteristics of the building and the damping and the input spectrum. Now we also have some coefficient method, approximate method with some kind of amplification factor 3. So you have the floor level acceleration for the given frequency. If you talk, you have the spectrum on the right side. Then C is the amplification factor based on the height. So that ratio of the heights are considered, and you can get the for a given damping frequency in the spectrum you take. Then do all this calculation. Repeat all this calculation for all the frequency. Then you will get the spectrum on the right side down. You have the red one. You can see that the energy of this particular simplified method of the spectrum is much higher than whatever the spectrum you get from the direct method or simplified method explained earlier. But that's the reason what I want to say, that for the beginning point of view, beginning of the design of equipment piping system, this method can be used if you do not have detailed flow input motion for equipment piping system. Also, I just want to see how complex you can follow. In this particular slide, I again want to emphasize that when you have very complex structures, you can have a simplified models, you can have a 3D models, you can try to generate. But one important point, you can see that peaks as you go upper side of the building, you have the very, very narrow band response spectrum. When you keep coming down, you have wide band spectrum. So what I want to say, the frequency keep on filtering as you go upper side of the building. When you go to the top, mostly it may be the first fundamental is going to govern the response spectrum of that particular floor. Hence, the input motions for that particular floor are mostly governed by the fundamental frequency of the structure. That's what you can see from these three spectrum on the left side. So if you see the top one, you have only one peak. When you come to the next one, you have two peaks. When you come to the down and down, you have many peaks. As I said, 0.1 to 50 hertz or 100 hertz. All the frequency components going to be there when you come to the ground levels. Please note down that is a very important point. Now, I just want to say the interactions. I'm going to talk more details on the interactions. As per our coordinators, that this particular audio is not there, but I'll try to explain this. So this talks about a very stiff soil as well as soft soil, and conventional building systems on the soft soil, and the reactor very safety related industrial systems on the rock side. And they try to say that the displacements in the soft soil is very large, and the frequencies are at say lower frequency long period waves are going to be there in the soft soil case as usual. Then we talk about the rigid structures. When you talk about rock side, you have the high frequency component, and the displacement of the structural systems of non-industrial or industrials will be very small compared to the structures which are kept on the soft soil. That's what we want to try from this particular animation on the video. Now coming to this, everybody is very conversant or very familiar with the soil structure interaction. So first we talk about 1893 spectrum. You have the spectral shape. If on the right side, middle one is not with the 1893. On the right side, I have shown for two cases. One is medium soil, another is the rock. You can see that the medium soil and soft soil shifts toward the lower frequency. That means long period side. So your wave characteristics have long periods. Therefore, your input motion, whatever going to come to the structures, also will have the long period. That's how the spectral shape shifts towards the lower frequency high time period. So that's how the soil is going to have the interaction effects. Now if you want to, if you don't take the soil structure interaction, for example, now if you just design as it is without considering, now let's assume that it is only rock site, it's a very hard soil, you don't have much interactions. Then if you have without considering, even though there is an interaction, but you are going to have certain cases, you are going to have the lower loads, and hence the design is not safe. In certain cases, maybe the design may be adequate, because in for example, if you talk about in the red lines, whatever I'm trying to show, when the frequency is say lowered, say for example, so initially without soil structure interaction you have the first line, but when you take the soil structure interaction, then the response comes down, but the displacement increases. But other side, when you take the blue ones, when you have the say frequency on the last line, if you consider it is, say for example, maybe 12 hertz or 13 hertz or 15 hertz, then when you have the soil structure interaction, it's going to come down the frequency. So your acceleration attracted is going to be very high. So this is one kind of interactions in terms of the responses. If you take the soil properly, then your response are different than without taking the soil. Similarly, equipment and piping, if you don't consider, you have the different kind of effects. That's what I'm trying to show from this slide. So where people are very much familiar. Now we talk about, please keep in mind whenever you are trying to generate the input motions for the floor mounted say equipment piping systems, you are going to have the response spectrum that has the peaks, spikes in the response spectrum based on the natural frequency of the structures. That shows that the natural frequency of the structure you should estimate properly. Say when you talk about the interaction in terms of the frequency of the structure by coupling and not coupling, then that is a valid point. So how to take care of that? We have certain guidelines, and what is the meaning of that? What are the limitations? And how with the different complex structures, how you are going to consider that kind of criteria, we will try to understand here. Now you have a single structure as I shown in the figures, and you have a structure is supporting on the supporting the equipment, then there is certain amount of interaction. But if you have a 2 or 3 substructures on the same foundation, you have the different interactions. When you have a single structure on the same foundation, you have different interactions. When you have the complex structure with the substructures on the main structures and have a common foundation, also you have different interactions. Now we are talking interaction with respect to frequency, because you understood that frequency is very, very important in terms of the whatever the design inputs you are going to generate for floor mounted equipment piping system. Now I try to explain here. Say elephant, I think very standard way. The piping components are very small. It doesn't have much weights like ant. Piping systems are small things like ant on elephant, because elephant, I want to say the structure is definitely elephant is its mass. Even say non industrial systems or the industrial systems, maybe the ratio of the if you talk about say I said no, there are 100 square meters, you have 10 tons. If you take total structure, even maybe the total non-structural element in the building may be about not even 10% or so, very small. Even similarly in the industries also you'll find, except whatever I shown, very typical cases like cement industry or the reactor buildings of the nuclear power plants, certain exception leaving that, otherwise you don't have much mass of the equipment onto the structures generally compared to the weight of the structures. Now you have the structure, so you have a heavy equipment sitting there, then the behavior of the without equipment is different. Now I try to show on the a tree, and you have the say I want to draw in the more bigger way also. Now let us imagine, I hope most of the people must have played something. I think those are coming from the villages. They generally go to the banana tree, and you have people trying to play on the tree. One person go onto the one branch, and other person is sitting on the other branch. He try to disturb that branch so that other branch gets vibrated and he try to fall. Such kind of place, anyway, I had experience. So with that experience, I try to have this particular picture. Now when you have a huge animal or a maybe huge bird, when try to vibrate one branch, definitely is going to affect the some amount of behavior of that particular branch where other person is sitting, other animal, other bird is sitting. There is going to be interaction with the same common foundation. There is a possibility is there. Depends upon how big this disturbance is going to come. Similarly, in the case of industrial structures and equipment, depends upon how big the component and how the foundation, how the next substructure is going to interact with this. That's very important to understand very clearly. Then they try to take these coupling effects to have proper modeling and predicting the frequencies, hence proper inputs for the, say, floor mounted equipment piping system. So what generally when I want to design piping and equipment system, so we'll talk a little more and more on the same aspect. So you have to have a certain equipment, you have a target to design equipment piping systems. Then you require to have the inputs. So we have the spectrum I mentioned. So that is generally broadened. I think now here I want to emphasize on what is the meaning of the broadening. With the considering this response spectrum, you do the analysis, get the force and moments on the equipment, and check the designs are safe or not. Now, why this flattening is done? You see, now we mentioned that I also try to explain the peaks of the response spectrum is generally at the natural frequency of structure. Now that uncertainty on the natural frequency are going to be there, mainly because of the soil structure interaction. I try to explain the frequency can shift either side of the whatever the spectrum, whatever the initial without soil effects. There's a shifting possible, frequency shifting possible. And same time there are numerical errors in the numerical procedures, modeling effects, many others, equipment structure interaction. All these things are going to be there. Some kind of gaps and errors are going to be there. To take care of the errors, the spectrum whatever estimated is broadened. So that's again this procedure we are going to give into the IS 1893 part 7 also. The broadening is mainly done for accounting for soil structure interaction, modeling effects, your numerical procedures. Then you have coupling effects of the equipment and piping systems. variation are always possible in structure frequency. Therefore, the peaks are broadened to take care of the spread of the frequencies. That becomes the design input for the structure equipment design. I think other parts is not, you can always understand easily. Now coming to this, we also be very careful in applying this kind of criteria because our industrial structures are not that simple. Even I think nowadays office buildings, even say, residential buildings are not very simple. They are definitely very complex. They are going to be, we have so many wings in the same building, but they have, maybe the expansion gaps must be there, but sometimes you don't have expansion gap. There is always a possibility of coupling effects. Now we want to design some important system on different floors. We have to take these particular aspects very detailed. Now, so the criteria, whatever we try to have, so this on the top side, whatever the criteria in terms of the mass ratio and frequency ratio. On the x-axis, it says the mass ratio of the equipment to the structure mass ratio. And the vertical axis, y-axis, is the frequency of the equipment to the frequency of the structure, say modal frequencies and modal mass of the structure, which represent as a two single degree of freedom systems or two spring mass systems as shown in the figure. The top one is equipment, the bottom one is structure. This is structure mass, this is equipment mass. So in this case, directly you have the mass of this equipment divided mass of this. That's what you are plotting here. And the frequency independently what you calculated for the equipment and the structure, you are plotting here. The zone, whatever you are seeing here, this side, if the frequency ratio and mass ratio is falling in this region, then you no need to couple, and that's not going to have, that means that is not going to influence the frequency change of the structure. That's what it meaning. Now, other side, on the right side of this curve, if these ratios are falling, then you have to say that it has to be coupled. And what is the meaning of that is that that's going to have the influence on the change of the frequency of structure when you couple the equipment. Now you have the two criteria. One is the AAC, another is the ASM criteria. ASM is the envelope of the AAC, little conservative. That was initially very when this is have certain kind of mathematical formation, but this is on case by case. They studied with the different mass ratios, different frequencies, etc. They consider, and they have this kind of criteria. On the left side, if the ratio is false, then definitely no need to worry about it. That is what a ant on the elephant. So it's not going to influence the structural behavior. When you go to the more than 10%, you have to consider the interactions. And also in the resonance zone, that at the frequency ratio of close to 1, in that zone also you have to consider the coupling. That's what we try to say. That's particular criteria you have to follow, whether the interaction effects in terms of the frequency are significant or not based on this particular criteria. And the basis of this criteria is, again, how much you are broadening. So here we broaden 10 to 15% on either side of the peak. So that same criteria is adopted, and this particular bounds are plotted as a limits of coupling and decoupling requirements. Now that is very simple when you have a single spring mass system or a single structure, and that is a independent, doesn't have any substructure connected to each other. Very easy to apply such kind of criteria. Then we have a lot of with other researchers also we have done good amount of details on this. Now if you have the branches like this in the same structures, I think most of the industrial structures, even as I mentioned, even office buildings nowadays you have, and there is a possibility that these substructures have a different characteristics. Sometimes only one substructure may participate or vibrate in certain mode, sometimes together, sometimes other one, sometimes part of the structure may be coupled with the other substructures. These kind of situations are going to be there. Then what is the mass ratio? That's what clarity generally people are missing in the most of the practicing engineers. So I want to make it clear that you should evaluate what is the DOF mass. When you're trying to take the mass ratio of this particular modal levels, you calculate what is the DOF mass. Now based on the DOF mass of the each substructure, again you can check with the ratios and see that whether coupling is required or not. So the difference when you have this kind of substructures on the same common foundation, and you want to have the inputs for a certain part of this particular whole system, then you have to take the this criteria very carefully and evaluate DOF mass of these substructure and take the ratios with respect to the equipment supported structure correspond to that particular equipment, and see that whether coupling required or not. So that is very, very important. That's what I'm trying to say. Now when you have the two branches, when you have a huge monkey sitting on that, depends upon the monkey how it's going to vibrate. If it's very heavy, it can also can disturb other side branch, but it is separated. These branches are separated, at the say foundation level. So that kind of things you can easily physically understand, and that's going to be there even in the case of structures. Now, other part is, is so it's not that always it is equipment are going to be supported at one particular point or one particular floor, but the equipment also going to be supported at a different location of the structure. For example, say cement industry, the main cement industry plant, whatever you have. So you have this particular equipments, even silos and the ducting system is having supports at different places. It's not that this silo is just supported at one level and left as a cantilever. In this case, the stiffness effects also going to come into consideration. Just following that particular previous criteria is not enough, because you should have the stiffness effects also there. Mostly significantly, the frequency effects are there, how close they are with respect to the supporting structure. But here the stiffness also going to play a very important role. We try to develop some kind of criteria into this. And you see the criteria is entirely different from what you have seen earlier in this particular picture. So the hatch portion where you require coupling, but below you don't require coupling. But at the again frequency resonance kind of conditions, a small band you require to have the coupling, otherwise don't require coupling. Then again you have mass ratio and frequency ratio. So the criteria becomes different when you have a system connected at different location. That this criteria again is meant for when you have the component is connected at two locations. So the such kind of clear criteria you should use in order to check the coupling effects in terms of change of frequencies. That change of frequency has a significant effect on the structural response as well as the response of the equipment which you are going to design based on the flow response spectrum. That's what the interactions we try to explain now. So I think I hope very, very slowly we went to the complex thing and tried to explain what are the interactions. I hope people are getting, I hope people must have got what I have explained so far, what is meant by interaction effects, how to take the interaction effects in the design of structures, equipment, piping systems. Now here I just want to summarize that first, you have the mod structure, then you have equipment piping system, then you want to design the equipment piping system, you generate the flow response spectrum using the direct methods or simplified methods, or you even to start the design you can use the coefficient methods, or if you have big computer, you have all the details in the beginning itself, you can have couple whole systems and the structures. Not that small piping and all, need to consider at least major equipment has to be coupled together and do the complete analysis and get the design inputs for other systems which are not considered coupled way. Now, also here, one thing you should keep in mind, when you are trying to design this particular floor mounted, even though you consider coupling, but when you want to check the design, you have to check the design again considering the uncoupled way the spectrum, because the spectrum considers when you say broadening, you are taking uncertainties of the soil structure interaction, modeling effects, and the numerical procedures we have, and interaction because of the other systems also taken into consideration, and you made the broadening of the spectrum. That aspect will be missing if you just take the response, coupled response of the equipment piping and say that design is adequate. That's not enough, because that's not going to take care of uncertainties, whatever meant for. Now the structure, this uncertainty is not going to matter much, because the spectrum, a small change in the frequency is not going to have large response variation in the structure, so it doesn't matter. But floor mounted equipment piping systems are very, very important. Even though you get the response design inputs for the say piping equipment can be coupled away, but finally you have to check all these important structure equipment piping systems using the spectrum in the uncoupled way also, and check the design is adequate or not. Now coming to the say piping systems, like again very good example is a fire water system or water supply system, even drainage piping system in the buildings, offices or residential building you want to design. See, it is now there is some kind of discussion always may be required when you are designing a structure as per the codes. We are just trying to avoid the collapse, that's all. Now in that situation, the kind of deformation, the deflections in the buildings will be very, very large. Suppose use the reduction factor of 5 or so, whatever elastic displacement you calculate, you have to multiply 5 times, then you will get so much displacement. When you're trying to impose on those displacement on this multi-supported piping system, if you want to ensure the safety, is a very difficult task. So it's possible to design, but now when you say collapse prevention, whether only target is to see the save the life. Now if you want to leave or you want to continue, or only the purpose is fire safety, secondary hazards point of view, these systems has to. So you have to really have a lot of debate and see what level of designs, up to what level you consider, what kind of inputs. Definitely you have to have the proper selection. Now, the piping system, when you want to say, so you required not only the say spectrum, but also you require the flow displacements. You have to apply as the anchor moments, and you have to do the some kind of multi-support excitation for these piping systems or equipment running at different force, and evaluate the forces because of the anchor moment, because of inertia, and appropriately combine and check the design limits are within the acceptable limits or not. So briefly, as I mentioned in my abstract, briefly I just touch only maybe 2 slides I have. Is the time is okay? I think organize. Hello.
Yeah,
I think
you can. Yeah, am I audible, Professor Reddy?
I exceeded a little more time, so I'll just one more slide. Yeah,
Sure,
I
yeah.
think only one slide. Yeah, one more
Sure.
slide. So I just briefly explaining about part 7. So we are bringing out this particular standard with the different inputs. Scope very clearly mentioned is this particular part is valid for applicable for the non-active components and components like rotating machinery and all not touched in this. Then we try to explain terminology like MC, DB, then what the response spectrum, time is all the terms whatever regularly you see other parts of the IS code also explained here. And categorization is very, very important here. As I said, so again, if you recollect, LG polymers of Vizag, so that kind of accidents happens because so you have to put the proper categorization. So category 1 kind of things how to design. Then what are the inputs? What are the reduction factors? What are the importance factors? We try to give all the details here. Then section 1 talks about the equipment, design load combination, design inputs, whatever explained so far. Different time history methods or direct methods or coefficient methods we can use to generate the design inputs. Numerical models, what are the things to be considered? So damping values, then load combination, everything is talked. And design checks, what are the limits for design checks also given. Active equipment, how to qualify by test also dealt in this particular code. And section 2 is the piping systems. Again, criteria, design criteria, the importance factor, performance limits, what you are expecting, design inputs, as I said. Here you have the addition to the, say, inertia part, you also have the anchor movements. Then how to evaluate inertial effects and anchor movements responses. Then we have a lot of annexures, generation of time histories methods. So I was explaining power spectral density methods, even compatible time is how to generate. Those things are there. Examples on the finite models, selection of number of modes also given with examples, method of analysis, generation of flow spectrum with examples also given. So, and compatible time history generation methods also given. So overall, content of the IS 1893 part 7 is this, that will try to take care of whatever I try to explain. That is small part, whatever explained is the interactions, is small part of this whole design, standard IS 1893 part 7. So now I think last slide, I think this is what out of my maybe thinking I have. So I could see this, what is that called, mangroves. So mangroves growth, it shows a very interesting feature. So it has a low inertia, high energy absorption, high redundancy, high flexibility, high bearing capacity. And the bearing capacity keep on building as the time passes because automatically the roots keep on expanding and expanding. What I want to say, in our structural design, in our non-industrial systems or industrial systems, when you are trying to design, see that these parameters are built in the design so that you have good safety and you have very, very low risk, particularly for the earthquake, loads. You have low risk and you have a better living. Thank you so much. That much I want to, present here.
Okay, thank you, Professor.
I hope all of you enjoyed a little bit. Let us see. Yeah.
Yes, we are receiving several messages of your presentation.
Okay.
Okay. So we will go for the question and answer quickly, sir.
Please.
Yeah. So I am taking the first question. What are the criteria or procedures to discretize the flexible piping and equipment into lumped mass and spring system, and how to calculate the damping constants? How to consider the coupling between the and structure interaction. There is another related question to this. How can the masses associated with concerned degrees of freedom, especially torsional and axial degrees of freedom, be calculated for developing a simplified model?
Okay. So first question is on the coupling, right? So if I understand the coupling between the piping and equipment, that's what I understand. Am I right?
Yes, lumped mass modeling and how to consider coupling.
Okay. So see, I think I hope the person asked this question will have has some amount of experience with respect to dynamics. So the inertia in a particular earthquake response calculation, the inertia plays very important role, and the mass movement of inertia little bit, but definitely not so much. So lumping is always accepted even in the piping systems and equipment system is not a problem. But you can have the consistency mass matrix also is not a big deal at all. Now when you coupling, if you want to say, now coupling, let me separately talk about. One is piping, whether piping has to be coupled to the equipment or not. Definitely piping, you don't need to couple with the structure, as I said, if because the piping inertia and the amount of force is going to come onto the structure is not going to be so significant. There are going to be good amount of reactions, but that is not going to influence the behavior of the structure. Therefore, coupling of the piping with the structure may not be required, but coupling of the piping with the equipment may be required. Now, whether to couple the piping with the equipment or not, now one should be very careful. The criteria what we have explained is we have a all the characters of the equipment and the characters of the structure is like more like singly coupled system. Or if you have equipment connected two locations, you can have the criteria whatever we try to give in the next next presentation after the first presentation whatever I have. But one should be careful. If you have a connection in different locations also, one should be very careful in order to choose that particular criteria. Definitely well clear. If you have a branches also, you can have the degree of freedom mass. When you have a only one cantilever structure supporting the main equipment, you can have that concepts of criteria you can adopt to see the frequency effects. And how much effect on the inertia or the total response not clear. There is going to be either reduction or increasing. So that's what I try to explain on the response in terms of the acceleration and force and movements. But frequency effects are very important because that has a further effects on the floor mounted equipment and systems design. Therefore, the frequency effects are concentrated and taken care in the criteria. Now coming to the piping, the same criteria you cannot adopt. Very clearly you should see the interactions of the equipment and piping. If you want to see the same criteria you want to adopt, that's sometimes I saw the some of the engineers try to do the same criteria, but we cannot do that because the basics of that particular criteria is started with single degree of freedom structure, single degree of freedom equipment only. It's not that you have a piping support at different locations and equipment also has a cantilever or support at different locations. You cannot adopt the same criteria. So please note down that. In this case, now we have a piping and to see that all the degree of freedom is constrained before the connection connect to the equipment. Then you can isolate that. I hope I am explaining. Now you have a piping. I do not know whether I can draw it or not. You have equipment. Then equipment is connecting the piping system. Piping has different supports. But the piping, when you come to say you start from the left side and you reach the right side where the equipment is there, by the time you reach, if the piping is already constrained in all three directions, definitely you can decouple the piping from the equipment without much problem. And second one is the movement of inertia. I said no because stiffness is going to play a very important role. If I remember, if the movement of inertia of the equipment and the movement of inertia piping is less than 100, then what I want to say, the movement of inertia of the piping is 100 times less than the equipment. You don't need to couple, but it is lesser than that. You have to couple see the stiffness effects, and that also going to have the influence on the overall frequencies and the response. I hope I explained that.
Yes, Mr. Reddy. Yeah. So next related question is, if there are 3 to 4 equipment supported on the same floor,
yes,
how should we consider the mass ratio to decide the coupling criteria?
Okay. So let us talk about 4 equipment have a different frequencies. Let's talk about 4 equipment on the same floor but different frequencies. If you have a same frequency, then take the total mass of all the equipment, then take the ratios. That is, I think, very clear to the people. But if you have a different frequency of the equipment, Now, when you talk about the mass of the structure, you have to take the remaining, say, take one equipment, remaining of 3 equipment mass you take on the structural mass and take the ratios of the frequency and mass. And similarly for other things also you can check and see whether coupling is required or not. I hope I explained that.
Yes, Professor Reddy.
Yeah.
Next question is there any role of damping the non-structural components, and how to consider it while performing time history analysis? And yet another question probably related to this is secondary system themselves may act like a tune mass damper. They can have their frequency matched with one of the model frequencies.
Yeah.
What will be the effect of the interaction between the equipment in secondary structure and the main structure?
Yeah. So again, I think first we'll say damping. This criteria is independent of the damping, whatever, because that criteria is only meant for the effects on the frequencies. So whatever the damping shift in the frequency, there is a reduction possible if the coupling is there, then there is a coupling damping, right? It's modal damping. You have someone to suppose you have structure 5%, you have piping is 3% or so, the modal damping may be higher. You can take into consideration because you are telling that they are behaving coupled way. No doubt you can take care. Okay. Now, if you want to just see that frequency effects are there or not, then damping is not playing much important role. Only see that when you couple it, there is a change in the frequency or not. That's all. I hope I answered that. But again, I want to say, I want to say one second. I want to say again that when you talk about coupling is required, then you couple the structure with the equipment or equipment with the structure, do the complete analysis and generate the design inputs at the different floors. Now, if you don't take, as I mentioned, I hope people got it. See, the uncertainty effects on the structural response, uncoupled structural response, not very, very high compared to the equipment response. When you couple it, there is a significant difference is there. The reason is that in the ground, when you talk about, suppose there is a 10% frequency variation of the structure, say 3 hertz, it becomes say 2.7 hertz. The acceleration variation is not very high. So what I want to say, the response because of the coupling effects influencing the total frequency is not much on the structure. But if you go to the different floors, if the shift in the frequency, say 10% or 15% because of coupling, then you can see the response variation of the floor mounted equipment is very, very large. So that makes a lot of difference. So the uncertainty effects, even though you couple the equipment and do the response calculation of the equipment, but it is suggested to take uncouple the response spectrum generated with the coupling effects, but that input has to be further taken for the checking of the design of even coupled equipment. That's what I wanted to say.
Yeah. Another part of this question was the secondary equipment or secondary structure itself can act as a tuned device in one
Yes.
of the
Yes. Now that's what that's again there is a possibility of a response reduction in the even structure, but the amount of mass what we are talking about, equipment mass. Now if you see the total mass of the structure, we're talking about some effect you have a 10% or so. That 10% mass is when it's tuned, you have a significant effect if you have a harmonic excitation as absorbed. But in the case of random excitation, you don't have that kind of, yes, there is a possibility in that absorbing frequency range, that's when frequencies are matching, there is a reduction in the response, but you cannot see so much like harmonic excitation. That's what I could see. Yes, there is a, if you want to have a retrofitting or requalification of the structures, definitely you can take advantage of this absorption effects. Yes, please. You can definitely take that. Yes.
Yeah. The next question is, if we provide isolation to the structure, then in that case, do we have to really worry about the design of piping or equipment system, or for non-industrial case also, if we provide some isolation system, shall we really worry about design of the equipment and the non-structural elements?
Yes, I think okay. That I think when you talk, maybe when you talk about base isolation is good. I think you don't see much force on the floor-mounted non-structural elements or equipment pipings. But differential displacement is very important for running the your whatever the services like cables and piping systems. all the control electronic systems, your cables, everything running from one building to other building, the differential displacement becomes very important to consider in the design. That's definitely required, even in the base isolated structure. But now also one should be careful if you have a liquid tanks and all. When you have base isolation, yes, frequency lowers. You have to ensure that it's very easy to shift the frequency of the liquid sloshing and all. So one should take care. But definitely isolation is a good concept. One should adopt in most of the places. But the technology, it's still, when we trying to we try to particularly I have put a lot of efforts to see that in the nuclear industry this technology can take up. But I think slowly is picking up now. That's a good concept one should adopt. And piping, particularly the systems running from one building to other building, you have to be very careful in the design. That's all. Anything else, please?
Yeah, so the next question is related to the comparison with the ASCE 7. So how does our code compare with the upcoming part 7 compares with the ASCE 7 provisions?
Yeah, I'm still, I think you also part of that, so we should do that. And I think whatever so far covered, maybe concepts are we're trying to have the same, but one-to-one comparison we'll do that. I'm not done. I hope we must be doing that, so we'll discuss.
Okay, thank you. Okay, and then several participants have asked, when do we expect part 7 to be released?
Oh yeah, now I think we should work very hard, and is almost, I think we have done it now. Only we are stuck with
Yes,
load
yes.
combination stress limits in the piping system.
Yes,
Except that,
yes.
I think we are all through. If that is there, then I think let's target in this year. I think
Yes,
possible.
yes, sure, we will do that.
You also should commit that.
Yes. Right.
Yeah.
So actually there are several other questions, Professor Reddy. Time is running short, so we will have to now stop. So I am handing over charge to Professor Kolathaya. Thank you once again for your wonderful talk and interaction.
I hope people enjoyed. I hope so.
Yes.
Professor Kolathaya.
Thank you. Thank you, Dr. Rosan.
Yeah.
Thank you, Professor Reddy. Excellent presentation. It was a very lucid presentation, and you have made a complicated problems and concept in a very simple forms, like your examples, mangroves. Your vast experience now was reflected in your presentation. So I am sure all the participants, especially the students, a lot from your interaction. So thanks a lot, sir.
Thank
and
you so
special
much.
thanks for your willingness to come for the webinar in spite of the schedule, and your cooperation also, because we had to change the also, no?
No,
So
all
your
fine. But let me say
very
thanks to all of you. Dr. Vasant Matsagar, Dr. Ravi, and Dr. Srivalsa. Thank you so much for giving this opportunity, and for ISET also. Thank you so much. And thanks for, I hope a lot of people registered, I think so. Thanks for everybody for participating in the presentation.